In this video, I'd like to talk a little bit about the second law of thermodynamics and give a simple model of how two systems will tend to exchange energy and move towards the most likely macro state of the system. So what we have is a statement of the second law of thermodynamics, which says that systems tend to move towards the macro state with the largest number of microstates. And remember, when I say macro state, that I mean the distribution of energy between two objects, right? So I have two Einstein solids. The macro state is the number of units of energy in Einstein solid 1 and the number of units of energy in Einstein solid 2. Each macro state has an associated number of microstates. So to demonstrate how this energy can move back and forth and lead us to a state with more microstates, the more probable macro state of the system, the more probable distribution of energy between the two, we're going to play a little game, and the rules are we are going to move step by step, and in one step we can exchange no more than 1 unit of energy between the two Einstein solids. So for example, if we start in this microstate and we want to take one step, we can either have Q1 give a unit of energy to Q2, bringing us to this macro state. We can have Q2 give a unit of energy to Q1, bringing us to this macro state. Or we can have no units of energy exchanged at all. And any of those would qualify as one step, right? And the other rule is that for each step, every available microstate has the same probability of occurring. So what that means is that if I start here, any available microstate in any of the 3 macrostates that I have accessible to me in that step is equally likely to occur. Let's assume that the system begins in the least likely macro state. That is the macro state where 7 units of energy are in Q2 and 0 units of energy are in Q1. I have labeled the macro states A through F just for simplicity. There are more macro states where I could keep trading energy back and forth, but we'll just focus on these for our purposes here. Okay, so let's assume that we begin in state A, and we allow ourselves to take one step, which means at most we can trade 1 unit of energy from Q2 to Q1. We obviously can't give more energy from Q1 to Q2. So our possible final states are A and B. Now, assuming that every microstate is equally likely, we can calculate the probability that we will end up in state A after we take a step or in state B. Probability that we stay in state A is the number of microstates in state A divided by the total number of microstates available to us while we take this step, which is just the sum of the microstates in A and B. Okay, adding them up, there are 1,800 total microstates, and 330 of them are still in state A. So that leaves us with an 18.3% chance of taking a step and not having Q1 gain energy. While the probability of ending up in state B, where Q1 has gained energy, is in fact 81.7%. So what we have learned here is if we start in an unlikely state, a state with not many microstates, that taking one step, exchanging some amount of energy, will lead us to a state which is more likely, which has more microstates associated with it. Now let's imagine that from starting in A, we ended up in macro state B. So we started in A, we took a step, there's an 82% chance that we landed in macro state B after taking one step. Now let's take another step starting in state B. So we can calculate the probability that after starting in state B, we will end up in state A, state B, or state C. To do that, we simply take the number of microstates in whatever we're interested in. So for example, B, we take the number of microstates in state B and divide it by the total number of microstates available to us while taking this step. This leads to 1,470 microstates in state B. Our total available microstates is just the sum of these three, which is 5328, and we get about a 28% chance that we take a step and we stay in state B. However, if we want to see what is the likelihood that we'll move from B to A, well, now we only have a 6% chance of doing that, because in this step we have access to all of the microstates of state C now, which is a ton of microstates. So even though the individual microstates all have the same probability, right? This one has so many fewer microstates that it's just very unlikely we'll land there. It's like having a raffle where this state got 300 tickets and this state got 3,500 tickets, and this state is therefore much more likely to win that raffle, right? So the probability of going to state C is about 66% when we take this step. So what you can see is that if we start in state A and we allow some energy to be exchanged, right, we take a step, that we are very likely to end up in state B. And if we don't end up there on the first try, we end up back in state A, well, then we have to take another step. And when we take that step, we're again likely to end up in state B. And then when we're in state B, it's very unlikely that we'll go back to state A, and much more likely that we'll go to state C, which has even more microstates. And we could continue this process for each of the steps along the way, right? Go from C, it would be more likely if we were in C that we would end up in D. Why? Because D has more microstates than B and C combined. Now, because this system is so small, there's still a reasonable chance of moving from state B into state A, about 6%. That's pretty large in comparison to if you look at something like sticking two pans together, right? If I stick two pans together and one of them is super hot and one of them I just took out of the freezer, there's no chance that energy flows from the one I just took out of the freezer into the really hot one, and the hot one gets even hotter and the one I just took out of the freezer gets even colder, right? That never is going to happen. And what happens is that the statistics, when you have a macroscopic number of particles, right, like 10 to the 23 in Avogadro's number of particles, the chances that you move from a low probability state into an even lower probability state is vanishingly small. And the probability that you move into a higher likelihood state, like moving from state A to state B, becomes overwhelmingly large as you get a macroscopic number of particles.